Hey y'all, welcome back. Today we are reviewing for our Unit 8 test over geometry. Specifically, we're going to be finding the area between two curves. We'll be finding volumes of solids generated by revolving regions around both the x-axis and other horizontal lines. And we're going to find the volume of objects formed by taking a region and using it as the base of a solid that has a given cross-section. So this unit was a little shorter than some of the other units, but it's still pretty packed with different kinds of problems here. So let's, without further ado, let's go ahead and get started with number 1. It says let f and g be the functions defined by f of x equals 1 plus x plus e to the power of x squared minus 2x, and g of x is x to the fourth minus 6.5x squared plus 6x plus 2. Let R and S be the two regions enclosed by the graphs of f and g shown in the figure below. And before we get too much further here, we need to make sure that we know which one is f and which one is g. So we're going to go over to Desmos and type in these two functions. F of x was 1 plus x plus e to the power of x squared minus 2x. Oop, need that minus to stay up there. Anytime you have that sum or difference, sometimes you got to put that in parentheses when you're dealing with an exponent. It's a little quirk of this software. And then g of x was, let's see here, x to the fourth minus 6.5 x squared plus 6x plus 2. All right, so if we zoom in here a little bit, we can see that region R, which is that leftmost region, and the region S. And you know what I'll do to just make this even easier to look at is to restrict the domain of each one of these to go in between kind of this relevant domain that we're looking at between 0 and 2. So it looks a little bit more like the picture we see on the paper. Okay, there we go. How about that? That looks a little more like what you're seeing here, with region R being the leftmost region and region S being the rightmost region. And we do have that point of intersection. This was already indicated on the paper, but it's 2, 4. And this point right here is 0, 2. So let's go back to the question. So it says, for part A says, find the sum of the areas in regions R and region S. So going back to these two graphs, the whole reason we kind of put these in to begin with is to figure out which one was f and which one was g. And you can see that blue function there is g. So I'm going to go ahead and label that here, actually in blue, just to stay consistent there. So yeah, this one's g of x. And maybe I'll even highlight it just so that it's real clear. And then the other one was f of x. And I think it was in red, wasn't it? Yeah. So this one right here, that is my f of x. So the reason why it's super important that we know like which one is which is because at that point of intersection, which I guess we'll have to figure out what this is. Maybe I'll just call that A for now. The function that is on top is going to switch, like from between 0 and A, g is on top, but between A and 2, f is on top. So when we set up this integral, we're actually going to have to set it up into two separate parts, and let's go ahead and just write out what that is. So we've got the integral from 0 to A. Okay, so this is going to be that first section. In other words, this is going to be this area in here. I'm going to try to color code everything here just to make it real obvious. And so the top function here is g, and the bottom function is f. So I'm going to say g minus f dx. And then the second area, which maybe I'll do that in run out of colors here. Let's do yellow, or no, let's do orange. Orange is kind of close to red. Let's go ahead and stick with yellow. So for this area, area S, hopefully you'll be able to see this okay. I might have to switch out the color here, but we're going to say plus. No, that's going to be too hard to see. I'll just do it in black. Plus the integral from A to 2 of, and now in that second region, region S, you can see that function f is on top. So it'll be f minus g. And of course, dx. Now, this is going to be something that we could just plug into Desmos, but we do need to identify what that point of intersection is. So I'm going to go back and click on, it looks like I'm already clicked on one of these. Just hover over here, and I get 1.032. So let's write that down. A is 1.032. And so now I'm going to go back and really just type this whole thing into Desmos, and that should give me my answer. Now I'm going to, that's not what I wanted. Let's try that again. There we go. So we've got the integral. Let's say what A is, right? We said it was, what was it again? 1.032. And yeah, we're just going to declare that as a constant so that instead of having to type 1.032 over and over again, we can just type A. So we've got the integral from 0 to A, that 1.032, of g minus f. And it's going to give you a little error here. And it kind of like, to get rid of that error, instead of calling these f of x and g of x, I'm just going to call these f and g. And then Desmos will be happy with this notation. Okay, so that's the region R. That's the left-hand region. That's this region over here. And so we're going to add that second region from A to 2, which is the rightmost partition here, of f minus g, because over here f is this top one is f, dx. And there we go, we get 2.004. And that is the sum of both regions. Okay, part B says region S is the base of a solid whose cross sections perpendicular to the x-axis are squares. Okay, so with all these cross-sectional or all these volume problems, they're all going to be set up very similarly. And that is, we're going to have the, and maybe I'll write this up to the side, the integral from A to B of the area of the cross-section times dx. That's it. I mean, it really, I know that these problems can seem more complicated. And part of that challenge is coming up with a formula for that area. In this case, it says the cross sections are squares, right? So I'm going to just draw a square here. And we're going to be dealing with region S here. So like the cross-sectional side, that is the side length of that square, is going to be something like this with the square kind of going into the page here. Kind of hard to draw that out. Really don't like how that looks. But basically that line segment that I have drawn there in black, that is like this side here. Okay, now it's a square, so all the sides are the same. But that side length is going to be f minus g, because f is above g. So yeah, this is f minus g, and that's going to be the same for the other side of the square, because it's a square, so all the sides are the same. Now the way that we find area is by doing base times height, or when it's a square, both of those bases are the same. So it's just f minus g times f minus g. So our integral, our setup, will be the integral from a to 2. We already defined a, right? That's this value, 1.032, of Okay, the formula for area here is f minus g, that's the side length, squared. Okay, dx. Let's make that d look a little bit more like a d. And so now this is going to be what we type into Desmos. So I'm going to go back, set up this integral. We're going from 2 to a. We're going to integrate the square, which has a side length of f minus g. And there you go. Uh-oh, hang on. Do I have it backwards? Wait, is g below? Oh, what am I doing? 2 to a. No, that should be a to 2. There we go. That looks a little better there. 1.283. Okay. Part C, determine the volume of a solid obtained when region S, so same region, is revolved around the x-axis. So here, if I'm revolving this region around the x-axis, I'm going to have like a washer scenario where the inside circle is defined in terms of function g, this blue function, and then the outside circle will be determined using the function f. So yeah, my cross-sectional shape here is a circle with a hole in it. And so the way that we're going to find that area, which is, let me just sort of highlight it here on the diagram, on here, maybe highlight this too because we're finding that area, is going to be the big circle minus the little circle. So this area here is going to be pi r squared minus pi r squared with those radii being defined in terms of the functions themselves. So yeah, the big radius here, I'll call that r, is going to be defined, and we can see this over here, from here to here, is going to be defined by f. And then little r, okay, the little radius, here's little r, here's big R. The little r from here to here is going to be defined by g. So we have pi r squared times pi r squared, pi r squared minus pi r squared is going to give us our integral. So the integral from still a to 2, because we're still using region S, of pi big R would be f squared minus pi times the little r, which in this case would be g squared. Now, if this is a multiple choice question, then you're most likely going to see that pi factored out. So you don't really necessarily need to type it in this way or even write it this way, but just be ready on a multiple choice item to see this particular integral written like this, okay, with that pi factored out. You don't necessarily need to do that, especially like on a free response question, but you'll see it written like this if it's multiple choice. So let's go ahead and type all that in over here. I guess we can like keep what we have here, right? We're still going from a to 2. It's just that we have pi r squared minus pi r squared. So we've got like pi r squared minus pi r squared. Okay, and we get 15.533. Letter D. This is a region R. Okay, so now we're going to R now, and we're going to leave S behind for a little bit. Okay, so let me erase some of this just to kind of clean up our little diagram here. Okay, we're going back to region R. So region R is the base of a solid whose cross-section perpendicular to the x-axis are rectangles, whose base lies on the xy plane and whose height is 2 more than the base. So here we've got a rectangle. Our setup's going to be very similar to that of the square, except since the side lengths are not the same, we can't just do side length squared. We're going to do base times height. So we've got this rectangle where the base is like right here, the difference between the functions. Actually, that should be g minus f now, not f minus g. So let's fix that. So G minus F. And then the height is 2 more than the base. So we have G minus F plus 2. So the area of a rectangle is just base times height. So that's what's going to set up my integral. I'm going to go from, in this case, 0 to a. And then base times height would be base is G minus F. Height is G minus F plus 2. And this is something I'm going to type into Desmos. So yeah, I'm going to start a new one here. Go from 0 to a. And I've got G minus F as the base. And then the height would be G minus F plus 2. dx. I get 3.164. Part E, determine the volume of solid obtained when revolving region R. Okay, so we're still on region R like we were on part D. I'll go ahead and highlight these from the previous problems. So yeah, region R is revolved around the line y equals 3. So if we look back at this diagram, y equals -3 is like, not even to scale here, but somewhere down here. And we're going to revolve that region R around it. So like if I take this point here and revolve it around, that's what's going to give me the smaller circle. Revolving this around is going to give me the bigger circle. It's kind of messy, so I'm going to delete that. Oh, what did I just do? Let's shade that back in. Okay, don't really need that point there anymore. There we go. Okay, so either way, you can see that the smaller of the two circles is going to be defined in terms of F, and the larger will be defined in terms of G. So this is going to be another washer problem where we've got a big radius and a small radius. But we want to be very careful about which one's which. Find the area of like this outer circle. So the big radius is going to be in terms of G, but it's going to be, it's going to be a little bit more than G because the line that we're revolving around is below the x-axis. So big R and little r, okay, big R is going to be G plus 3, little r will be F plus 3. So we go ahead and set this up with the integral from 0 to a of pi r squared minus pi r squared. Now you can factor out that pi. You don't necessarily need to, but you can. So pi r squared minus pi r squared, all that times dx, which is the thickness of that washer, by the way. And this is something we could type into Desmos, which most of these problems should be. So am I just going to need a new one here? I guess so. Well, I'll just delete this one. We'll have one. This is going to be for our S. Here's for our R. So for this one, we've got pi r squared times pi r squared. Let's just delete all this because we don't need any of this. Oh, that did the opposite of deleting it. There we go. Okay, so we got pi times r, which that this function right here, this upper function is g. So we're going to have g plus 3 squared. Okay, pi r squared, so that's the big circle. And the smaller circle of that cross section is going to be pi r squared, where r is F. And so I get about 35.056. All right, moving right along. F, the region S. Okay, so we're back to region S. So that's going to go from A to 2. Models the surface of a small pond. At all points in S, at a distance of x from the y-axis, the depth of the water is given by function h. Find the volume of the water in the pond. Okay, so this is going to be another rectangle problem where the depth is given by 4 minus root x. So I've got this rectangle, and one of the side lengths is the distance between f and g. So with f being on top, g being on the bottom, this is going to be f minus g. So that's going to be like the length of that cross section. Okay, so it's going to be f minus g. And then the depth is 4 minus root x. And so each cross section is going to be a rectangle. So we have base times height here for our area of the base of the cross section. So we're going to go from A to 2, since we're working with region S. Base times height would be f minus g times 4 minus root x dx. And we'll, just like every other problem on here, we're going to go to desmos. And we're going to type that in. So I guess I'll just start a new one. Or you know what? No, let's use the S. That's this one down here. Let's just delete what we have in here so far. Okay, so from A to 2, we've got f minus g times 4 minus square root of x dx. I get 2.775. Part G says find the area in region S that is below the line y equals 2. Okay, so we're going back to an area problem here, kind of taking a break from volume. We're looking at region S, that's this region here, but what we want is the area below y equals 2. Now you can see y equals 2 is labeled here, but even if it wasn't, we could use desmos to find out exactly where that is. Here, oh, no, let's not use a highlighter there. Let's use, I'm running out of colors here that will stand out. Use orange here. Is that gonna, that's, okay, well, at any rate, here's where y is 2. So the area we're interested in is this area down here. And so this is gonna be another area problem, similar to how we solved letter A. Just our top function is gonna be y equals 2. And our bottom function is going to be g of x. So our integral will go from a to 2. Oh, actually, no, hold on. We don't actually know what that is, do we? We need to find what these 2 points of intersection are. What are these? So yeah, let's go back to desmos. Type in y equals 2 here, so you can see where that happens. And so that's going to be at 1.168 and 1.755. Okay, let's write that down. 1.168 and then the other one 1.755. And the top function is 2. The bottom function is g. So this is going to be what we type in. So let's go ahead and I'm just going to get rid of some of these just to give a little bit more space here. Oh, no, we kind of do want that y equals 2, don't we? So we can see a little better. Okay, so we've got the integral from, let's just hover over here to see 1.168 to 1.755. The top function is 2. And the bottom function is this blue function g. So 2 minus g. And we get about, we need the dx, 0.216. Really close to 217 if you want to round that, no problem there. But I'm going to leave it as 0.216. Okay, last part of this first problem. Cross section is perpendicular to the x-axis in region R. Okay, so we're going back to region R. Have an area given by that formula. So we don't really have an idea of what this cross section is going to look like. It could look like anything. Who knows what it looks like? But we do have the formula for the area. So that a of x, like this first part, in our integral over here, that's given. We don't have to come up with it. We don't have to worry about radii or side lengths or anything like that. We just are given that formula directly. So in region R, which was this leftmost region over there, here you can see in purple, goes from 0 to A. And our area is just 2 over 5 plus x. We don't have to investigate further, just dx. So we'll type that in. The integral from 0 to A of 2 over, I think it was 5 plus x. I'll double check, but I think that was right. And so I get 0.375. And yeah, that is what it was. So this would be 0.375. All right, well, that's the first page and done with problem 1. Let's move on to number 2. Number 2 says let R be the region in the first quadrant bounded by the graphs of 4 cosine pi x over 4 and x minus 2 squared as shown in the figure below. The region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in region R. What is the volume of the solid? So before, just like with the previous problem, I need to make sure I know for sure which function's which here. So I'm going to type both of these in to desmos. We don't need any of these anymore. Okay, the first equation was y equals 4 cosine of pi x over 4. And then the second one, y equals x minus 2 squared. Okay, so we can see that it's the quadratic function that is below the cosine function. So let's go back here and highlight each of these. I'll use the same colors as I had back over here, which is blue for the quadratic. That's going to be the bottom function here. And then I'll do red for the cosine function, which is this top one. So yeah, this top one is going to be the cosine of, we forgot the 4. Did I type that in? I think I did, but I might want to go back and check. And then the other function, this one's going to be the x minus 2 squared. Okay, so the cross section is an isosceles right triangle. So if I take a cross section, let's say like when x equals 1, okay, this is going to be the side length of that isosceles right triangle. So the right triangle is going to look basically something like this. I'm not really putting any depth into it, but this side length is going to be the same as this side length. And that side length is going to be the difference between the top function and the bottom function. In other words, it's the top function minus the bottom function. So for a right isosceles triangle, the dimensions here are going to be that red function. And maybe I should give these names. Let's let f of x be 4 cosine pi x over 4. And let's I'll put let here just because we're making this decision. We'll let g of x be this other one. That way we could just say like f and g. And And so the difference between the functions is going to be f minus g. So this will be f minus g, and so will this. And the way we find area of a triangle is base times height, and since we know this is a right triangle, we can use each of those two side lengths as our base and our height. So it's really just going to be 1/2 times f minus g times f minus g. So the setup here is going to be the integral from 0 to, it looks like they intersect at x equals 2, but we probably want to verify that. We don't want to just go based on looks, and sure enough, that is at 2, 0. So I've got from 0 to 2. So that's going to be, remember the way we set these up, it's from A to B, we've got the area of the cross section dx. So that area is going to be 1/2 times base times height, and both of those are f minus g, so we'll have 1/2 f minus g squared dx. So let me go back here. We said let the cosine one be f of x, so let's change this to be f, and this one will be g. And so our integral is going to go from 0 to 2, and we'll have f, 1/2, this is half base times height, area of a triangle, half base times height, and the base and the height are the same. They're f minus g. So f minus g times f minus g would be f minus g squared. dx gives me 1.774. On these multiple choice questions, I'll always be rounded instead of truncating. I know I've been really stressing truncating over rounding, but just be prepared on these multiple choice questions that they will be rounded. But yeah, so this is going to be 1.774, and so you're just going to pick the closest one, which is the rounded version of the exact answer. Answer is going to be A. Number 3 says, in terms of C, determine the area bounded by the graphs of 1 over x plus 2x. So we're going to pay close attention to this one. Y equals 0. Okay, y equals 0 is going to be the x-axis. And the vertical lines, x equals 1 and x equals c. So we don't know what c is. All we know is that c is bigger than 1. Okay, I guess what the whole point there is that the x equals c comes after x equals 1. So to find the area, we're going to do top minus bottom, and maybe we should type this in to see. I assume this function is going to be above the x-axis, but let's just verify that. We don't need any of these anymore. So the function we have here is y equals 1 over x plus 2x. Okay, and we're going in between x equals 1 and x equals c. So yeah, maybe I should type those in. X equals 1 and x equals c. We don't know what c is yet. That's what we're trying to find, I think. Oh, it's going to be in terms of c, so it doesn't really matter where it is. So c will set up a, is c defined somewhere else? Why is it doing that? That's weird. Can't define c? Huh, why is it making c, what is going on here? Why? Well, maybe I'll just give it another name, a. That's kind of weird. Oh, no, it's doing the same thing. Why is it not letting me? Oh, you know what? I wonder if it's just not going to let me do it. Yeah, it just doesn't like any of them. So that's okay. We know it's going to be, let's just let it be 2 for now, but we know that we can change this value. Yeah, that's kind of weird. I don't know why it's not letting me create a slider for A here. Oh, you know what? I could just do the slider here. Okay. So it's going to be some number after 1, so we don't know where exactly it is yet. But we want to find the area of the region bounded, looks like between, this area in here. Okay, so it's going to be between 1 and c, underneath 1 over x plus 2x. So we've got the integral from 1 to c of 1 over x plus 2x dx. And we're trying to write this in terms of c, so we're not really going to use a calculator here. We need to find the integral of that expression. So we're going to have to find the antiderivatives of what's inside that expression, inside the parentheses, and then evaluate that from 1 to c. We're going to use the fundamental theorem of calculus here. So the integral of, or the antiderivative of 1 over x is the natural log of the absolute value of x. And the antiderivative of 2x is x squared. And we're going to go from 1 to c. This is not the same c as like the constant that you would get in here that would cancel out. So yeah, it's just a different c. Kind of annoying that they chose c there, but can't really help that. So now we're going to substitute in both c and 1. So this will be the natural log of the absolute value of c. Now we know c is bigger than 1, which means it has to be positive. So we don't really need those absolute value bars there. We're just going to do natural log of c plus c squared, okay, minus the natural log of 1, which we know is 0, but I'm going to leave it like that for now, plus 1 squared. So we have the natural log of c plus c squared, and then we have 0 plus 1 would be 1. So we have minus 1. And there's not really anything else we could do to simplify this. So that's our answer. Number 4 says let f be the function defined right there for you, 6 over 1 plus x squared. Let R be the shaded region bounded by the graph of f and the horizontal line y equals 3 as shown in the figure. Determine the volume of the solid obtained when the region R is revolved around the line y equals 8. So y equals 8 is like up here. And so what's kind of tricky about this problem is that the function on top, which is the 6 over 1 plus x squared, ends up being related to the smaller circle, right? Whereas like this boundary, this y equals 3 line, that's what's going to be related to the radius of the big circle. So let's go ahead and set that up, right? Our cross sections are going to be these little washer looking things. Okay, but be careful about the radii here. The big radius is going to be 8 minus the value of this function f. So big R is going to be 8 minus f. And then little r will be this distance right here. Oh, hang on. I got that backwards. Gosh, I said it right, but I don't know why I did that. The little r is going to be 8 minus f. Big R is just going to be 8 minus 3, which of course is 5. That's going to be constant. Okay, basically the distance between here and here is going to be 5. Okay, so let's see here. So now we'll set up our volume equation here. So the integral from, we need to find these 2 points, don't we? We need to figure out where our boundaries are going to be. So we're going to need to type in 6 over 1 plus x squared. Don't need any of these equations anymore. So yeah, 6 over 1 plus x squared looks like that. And then we have y equals 3. Okay, so we're looking for those points of intersection. Oh, works out super nicely, negative 1 to 1. How about that? So yeah, so we'll go from negative 1 to 1. And so we're going to have pi r squared minus pi r squared, just like with any of these washer problems, where the big radius is 8 minus 3, which is 5. So pi times 5 squared, minus the little circle, which is pi times 8 minus f squared. Okay, so let's go ahead and type this in. I'm going to give this function up here a name so I don't have to retype that. We'll call that f. Don't really need to give the other one a name because it's just a constant. And so we've got the integral from negative 1 to 1 got those negative 1 to 1 from the points of intersection of the two curves, the curvy one in the straight line, of pi r squared, so pi times 5 squared, minus pi times 8 minus f squared. Going to need parentheses around that whole expression, and then a dx on the very end. And it's not going to like that because I labeled this as f of x, but to fix it, I can just call this f. And there we go. We get 83.321. Part B says region R is the base of a solid. For this solid, cross sections perpendicular to the x-axis are quarter circles with radii lying in the xy plane. So instead of having washers here, we've got these quarter circles, right? Where the radius here, and we're just looking for the area here, but the radius of each of these is going to be determined by the cross section of the in the region. So I'm actually going to erase all this, just kind of make this a little easier to look at. I don't need any of this. In fact, I'll erase that as well. So the quarter circle is really like, if here's a cross section, it's like, something like that. So the radius, the r right here, is just the difference between the two curves, y equals 3 and y equals 6 over 1 plus x squared. So it's just the difference there. Okay, in other words, it's f minus 3. So we're going to go ahead and do our integral from negative 1 to 1. I'll erase this just to clean up the diagram. Now it's a quarter of a circle, so it's 1/4 pi r squared. So 1/4 times pi times r squared dx. I guess since we're just multiplying all those factors, we don't really need the parentheses there, but it doesn't hurt to put them in there. Okay, let's go ahead and type that in and see what we get. So we got the integral, again, from negative 1 to 1. But in this case, we're going to have 1/4, because it's a quarter circle, of pi. And then r here is going to be f minus 3 pi r squared dx. So we get 6.067. All right, there's 4b. Number 5, a water reservoir has a height of 8 feet. The area in square feet of the horizontal cross-section at height h can be modeled with the function a of h. Given that a of h is 46.1 over e to the 0.3 h plus 2h, find the volume of the tank. Indicate units in your answer. Okay, so we're talking volume. The area of the horizontal cross-section is in square feet, so our units should actually be in cubic feet. So you can write it like that, or you can write it like this. Okay, let's just make sure that we have those units in there. So our volume will be the integral. Let's see here. The beginning height. What was the beginning height? 0 feet. Okay, right here, that's the beginning height. I'm going to go all the way to 8 feet. All right, that's the height at the end. And then a of x, our area formula, is going to be 46.1 over e to the 0.3h plus 2h dh. We need to know what that equals. Okay, let's type that in. We got the we don't need any of these anymore. We're working with a new problem here, obviously. And so we've got the integral from 0 to 8. We've got this fraction, 46.1 over e to the power of 0.3 H, although I think I'm going to write this as X. I don't know if it's going to like the H. Plus, we could try. Well, you know what? Let's try the H. Let's see if it lets us do that. I'm worried that it's going to treat that as a constant as opposed to a variable. But is it going to? Okay. All right. No, it worked out okay. 56.048. And again, those units are going to be in cubic feet. So if we're having like a little trouble here, kind of envisioning what's happening, we've got this water reservoir, right? We'll just call it, we don't know what it is, but draw it like a cylinder, but it's not going to be cylinder. It says the height, like it goes from 0 to 8. So we're going to basically like cut this up into cross sections where the area of each cross section is this A of H. Okay. So, if you having trouble figuring out like the 0 to 8, that's kind of what's going on here. Okay, well, that's it for number 5. Let's move on to number 6. Number 6 says, let S be the shaded region in the first quadrant, bounded above by the horizontal line y equals 3. You can see that up here. Right, here's y equals 3. Below by the graph of y equals 3 sine x. Okay, so that's going to be that function down below. And on the left by a vertical line, x equals k, where k is in between 0 and pi over 2. Determine the value of k if the area is 0.79. Okay, so let's set up our integral here. First, we're going to want to know, because we don't know what k is, but what we can figure out with desmos is where is this point of intersection? Okay, where is the upper bound on our interval going to be, our upper limit? So let's type those in. We don't need this one anymore. So we've got the integral, y equals 3 sine x is the first one, is really the only one we really care a lot about, and then y equals 3. And where is this point of intersection? It's going to be at pi over 2. So just to make this a little easier to look at, I'm going to cut this off, between 0 and pi over 2. Okay, so this is really the region. We have some other vertical line. We'll start at x equals 0 here, but we could definitely move this. We don't know where it is. That's part of the problem here, right? Is figuring out where this is with a fixed area. So yeah, this upper limit is going to be pi over 2. The lower limit is going to be k. So let's start setting up this integral here. Okay, so here's pi over 2. So we've got the integral from k to pi over 2 of top function being 3, bottom function being 3 sine x dx. So the area is 0.79. So we're saying it's approximately 0.79. Now, how are we going to find, there's a couple different ways we could do this. I think one way is going to be to use the fundamental, let's just kind of work it out that way. And then I think I have another way we could probably knock this out too. But let's actually find the antiderivative of this expression here, 3 minus 3 sine x. And we can plug in pi over 2 and k. I think that this might be the way to go. Although I have another thought about how we might approach this, just in a little different way since we're getting to use desmos. So if we use the fundamental theorem here, the antiderivative of 3 is just 3x. Antiderivative of negative 3 sine x, we don't need u substitution or anything because we don't have a composite function, is going to be positive 3 cosine x. And we're going to go from k to pi over 2, and we know that's going to equal 0.749. Left out the 4 in the previous number. Okay, and from here we could substitute in pi over 2 and k into x. So substituting in pi over 2, we're going to get 3 times pi over 2 plus 3 times cosine of pi over 2 minus, now let's substitute in k, 3k plus 3 cosine of k equals 0.749. Now, let's clean this up just a little bit. And what we want to do here is we want to try to, combine. Well, do we even have any like terms here? I don't even really think we do. But this whole expression here. And by the way, you know what? Cosine of pi over 2, that's just 0. So like this term right here is 0. You don't really need that term. I'm going to leave it there for now, but just know like that's 0 right there. But here, we're going to call this like our first function. We're going to say like this is, I don't know, like our y1 and our y2. That's what we would call it, like if we were using the TI-84s. Basically, we have these two different functions. And we want to know for what k value do they intersect each other. So I'm going to type in basically like y equals this, and then y equals this. With k, I'm going to actually use x. We're going to solve for x. I don't know if it's going to, we could try with k, but I think we're going to need to use an x in its place. So let's try to type all that in here. And I'm actually going to like delete these for now. So we've got 3 times pi over 2. And then what was the next term here? 3 times cosine of pi over 2. Now, you don't really need this one, right? This 3 cosine of pi over 2, because we know that equals 0. I'm just going to leave it there anyway, just to make sure, hey, I don't want to make any mistakes here. And then we're going to subtract 3k plus 3 cosine k. So I've got all this. Put all that in parentheses here. Minus 3k plus 3 cosine k. Now, I wonder if we can make this a function of k. I don't know if we can. We might have to change this to x, but can we go like f of k? Yeah, it will let us do that. That's pretty nice. Okay, so it's a function of k. If you're having issues with this, you could always just replace k with an x, and it'll kind of serve the same purpose here. But then our other function, which I guess I'll call g, I'm just doing it in terms of k again, I guess, is equal to the 0.749. Basically, you just want that horizontal line. And then we could see that they intersect right here at 0.400. So k is going to be 0.400. Now, the other way that I was thinking about maybe we could do this is like going back to like the very, we're gonna do some like on the spot experimentation here. Is going back to this very first equation and kind of doing what we did, but I want to know, can we get away with not doing the fundamental theorem at all and just kind of doing the same thing where we have like our two functions on either side and set them equal to each other, but write the left-hand side here as a function of k? I'm thinking maybe that might work. I don't know. Let's see. So if I do like f of k, let's get rid of these. We already know what our answer is going to be, so we'll know if we did it right. So f of k equals the integral from k to pi over 2 of, what was it again? 3 minus 3 sine x dx. Okay. Oh, this is going to work, isn't it? Oh, I love it. And then actually g, yeah, we already know what g is going to be. 0. That is awesome. Okay, so guys, you can actually do this problem without even finding any antiderivatives at all. Okay, you just have to define your function in terms of like the thing that you're actually looking for, which is this k. That is such a time saver. We're still getting let me double check there. I'm pretty sure we're still getting 0.400. Wow. So like all that extra work, I was thinking at the beginning. I mean, I even said something like, "Hey, I wonder if like we could do this a little easier." You don't actually have to go this far. You can just start here, throw in both of these sides. Just make sure you're defining your functions in terms of k rather than in terms of x. That might be like a step too far to like remember to do that. So if you forget to do that, you can always do it the way that I initially showed you. But either way, you get 0.400. Number 7, which integral represents the volume of solid revolution determined by rotating the region in the first quadrant, bounded by the graphs of f of x equals x cubed and g of x equals 4x around the x-axis. So really, we just need to make sure that we are picking the correct like top function, like which function's on top. So we got x cubed and 4x. And if this were a non-calculator question, I know the test I'm going to give you here is going to be all calculator, but this looks like this might be like a no calculator question on the actual AP test. And so if you're not sure like which one goes on top, you could just plug in a number, figure out where these intersect, because that the region's got to be bounded by just these. So, where is 4x equal to x cubed? Like, where does that happen? You can solve this for 0, like x cubed minus 4x equals 0. Factor out the x, we get x squared minus 4. You can see that we're going to get an intersection at x equals 0, and we're going to get intersections at plus or minus 2. So, yeah, since we're in the first quadrant, let's highlight that, the first quadrant, you can ignore the x equals -2. So basically, and we can throw this into Desmos just to verify, but I think what's going to happen here is we're going to have our 4x, which is going to be kind of a steep slope here. And then you've got your y equals x cubed doing something like, I'm going to try to sketch this out, like something like this, right? So we've got this intersection point here at 2. And since that's where it's going to intersect, if you're not sure like which function's on top and which one's on bottom, you can pick a number like x equals 1, plug it into both functions and see which one gives you a bigger number, right? 1 cubed is 1, 4 times 1 is 4. That means this one's got to be on top. This one's going to be on bottom. So then when we set this up, the integral from 0 to 2, we're going to revolve. So it's going to be pi r squared minus pi r squared. Again, we're going to have like this, it's going to be like a washer here. So like even if we go right here, this little point is going to be revolving like that. This point up here is revolving something like this. So we do have a washer problem. The area of this is going to be pi r squared of the big circle minus pi r squared with the little circle. Okay. With the big circle, that radius is going to be 4x. The little circle is going to be simply x cubed. So yeah, we're going to have pi times r squared, with the big r being 4x, minus pi times the little radius squared, which will be the x cubed. And all that, of course, dx. Okay, so we just got to find which one looks like that. Now, notice here, and I had mentioned this before, that usually when you have these disks and washer problems, anytime you've got like a pi that's a constant factor, on the multiple choice questions, it's always going to be factored out, or at least all the ones I've seen have been factored out. I guess it's possible it won't be, but if I was betting, I would say, yeah, it's probably going to be factored out. So we got 0 to 2, 4x squared minus x cubed squared will be x to the 6th. So that's really what we're looking for here. And it looks like our answer is choice B. Let's scoot that over a little bit. Nope, not gonna let me do that. That's okay. Answer is B. Now, if you want to avoid, since the test I'm going to give you is going to be all calculator, I would just like throw these into Desmos and kind of look to see which one's on top and which one's on bottom. But it is definitely doable without that. Okay, number 8. Functions f and g are given by root x and 6 minus x. Let r be the region bounded by the x-axis and the graphs of f and g. Find the area of R. Okay, so basically what we need to do is split this up into two separate regions. Right here, we'll split it up at x equals 4 and just find the areas separately. Now, the left-hand area is going to be the integral from 0 to 4, and we're just going to integrate that square root of x. You know, this could easily be a non-calculator problem, it's looking like, dx. And then on the right-hand side, we've got the integral from 4 to 6 of 6 minus x dx. Now, before I do that, or really before I do anything, I want you to just take a quick look at that region on the right-hand side here. Okay, this region over here. Guess what? That's just a triangle. So while you can go through the motions and find that antiderivative, it's probably going to be easier to just recognize that that's a triangle and just say, oh, well, that's just going to be 1/2 base times height. 1/2 times 2 times 2. Right? Because we got 2 and 2 here. You could do it the long way and say, okay, well, I'm going to value, the antiderivative of 6 is 6x. The antiderivative of negative x is going to be negative 1/2 x squared. And do that from 4 to x, and then plug in 6. So like 6 times 6 would be 36. 6 squared is 36 divided by 2 would be 18. So 36 minus 18. And then minus, let's plug in 4. 6 times 4 is 24. 4 squared is 16. Divided by 2 is 8. And so we got 36 minus 18. Well, that's just going to be 18. And then minus 24 minus 8 would be 12. 18 minus 12 is going to be 6. And then, oh, wait a minute. Back it up. 24 minus 8 is not 12. That's 16. What am I doing? So 18 minus 16, and you get 2, right? But if you just do half times 2 times 2, well, 2 times 2 is 4, divided by 2 is 2. It's so much easier if you can kind of get away with, if that region is a simple geometric shape, is just to use the area formulas you already know. It's not really worth doing all this extra work here. Even though you can definitely do that, but you got to make sure your arithmetic's good. This would definitely be like a non-calculator problem on the AP test. Again, my test is going to be all calculator for this unit, but you can see how on a non-calculator section, a lot of room for error if you do it that way. So yeah, just take advantage of the fact that that's a triangle and do half base times height. You're going to get the same answer. So you might as well take the short way out. Now to get that green region, there is not going to be a shortcut here. You're just going to have to use fundamental theorem of calculus to find this definite integral from 0 to 4. So you could type this, you could type this into Desmos. I mean, obviously we're going to have that on the test, on my test. But this could be a good opportunity just to practice this. The antiderivative of root x, since root x is just x to the 1/2, the antiderivative would be x to the 3/2. Divided by 3/2 would be the same thing as multiplying by 2/3. And we're going to go from 0 to 4. Okay. So going from 0 to 4, let's see, what would that be? Plug in 0 is just going to be 0. So if we plug in 4, you're going to get, let's see, square root of 4. Let's just type it in, or write it out rather. 2/3 times 4 to the 3/2. And let's see here. Square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. So you get 16/3 plus 2. 2 times 3 is 6. So you got 6 and 16 would be 22/3. Okay, now again, you could get away with putting this in the calculator, but that would be your answer. If you were to put it in, what would that be? Well, 21 would be 7, so 7 1/3 would be roughly about 7.333. Okay, and I want to encourage you to use a calculator here. Honestly, if you're preparing for the test that you're taking next class, I would just throw really all this in the calculator, but I thought that would be this was a good opportunity to kind of talk about, just taking some shortcuts and especially how you do that without a calculator. Okay, moving on to number 9. It says the region bounded by the x-axis and part of the graph of y equals cosine x between negative pi over 2 and pi over 2 is separated into 2 regions by the line x equals k. Okay, let's go back to Desmos and start typing away this, see what's actually happening here. So the function in question is y equals cosine x. So just go ahead and type that, y equals cosine x. And we're interested in this in the part of this graph between negative pi over 2 and pi over 2. So I'm going to put that in as a domain restriction, pi over 2 and pi over 2, just so we see only what we're looking at. Where is it? Hang on. Well, what did I do here? Did I mess something up here? I think I typed that in right. What is happening here? Hold on. Like that. But why is it not? Let me do the domain restriction. That's kind of weird. Well, let me go like from negative 1 to 1. Oh, wait a minute. Okay, I see. I know what I did. I went from pi over 2 to pi over 2. I'm like, where is the graph? It should be negative pi over 2 to pi over 2. Okay, here we go. Now, it's separated in 2 regions by the line x equals k, which is going to be somewhere in that region. Let's go back and read the rest of the problem there. So I've got, I just wanted to get a quick sketch down here so you can see like kind of what's going on. Right, so we got from negative pi over 2, which cosine of negative pi over 2 is going to be 0. And to pi over 2, also 0. So our graph is going to do something like this. It's not going to be like a semicircle, but it's going to kind of look like one a little bit. It says if the region of the area for between negative pi over 2 and k is 3 times the region of the right-hand side. Okay, so for just like if they were equal, then obviously k would be 0, right? Because this is an even function. I mean, you can see pretty clearly that it does have that symmetry. But no, it says the first region, the region to the left, is 3 times the region to the right. So we know that k is definitely got to be like somewhere over here. Kind of hard to tell exactly where it is, but it's saying that the region to the left, this region here, has got to be 3 times the size of this region over here. Okay, so if the area of the region between here is 3 times the area of the region between k and pi over 2, then what is k? All right, so let's set up a couple integrals here. So the integral from negative pi over 2 to k of this cosine x dx is going to be 3 times the integral from k to pi over 2, again, of cosine x dx. Okay, now I'm going to show you the long way, and I'm going to show you the short way. Okay, so the long way here is to use a fundamental theorem of calculus. So the antiderivative of cosine x is sine x, because we know the derivative of sine is cosine. So here we would have sine x from negative pi over 2 to k. And that would equal 3 times sine of x from k to pi over 2. Now we could sub in all those values, okay? And this I'm going to simplify as we go here. Substituting k, that's going to be sine k. And then substituting in negative pi over 2. Well, sine of negative pi over 2 is 1. So that's going to be minus 1. Okay. Oh, wait a minute. Is that right? No. Sine of negative pi over 2 would be negative 1. So we'd have minus negative 1 would actually be plus 1. And then, so that's what we have on the left-hand side. And then the right-hand side, we've got 3 times whatever we're going to end up in here. So 3 times sine of pi over 2. Now sine of pi over 2 is 1, so 3 times 1 would be 3. And then we've got minus 3 sine k. So if I try to isolate my sine k's over here, I'm going to add 3 sine k to both sides to get 4 sine k. And then I subtract 1 on both sides to get 3 minus 1 is 2. Then I can divide both sides by 4. Let's continue this up here to get sine of k is 1/2. Now you got to think about your unit circle. Okay, when or what angle measure is sine of that angle measure 1/2? So if you want sine to be 1/2, that means you want the y value to be 1/2. You want this to be 1/2, which means you want this to be root 3 over 2, this to be 1, and so that angle measure is going to be pi over 6, or 30 degrees. Okay, so that's kind of the long way to do this, right? This is how we could do it by hand. But we can also solve this using the calculator a lot faster. Let me show you how to do that. Okay, so if I'm going to go to Desmos, I can write both, and this is going to be kind of similar to how we solved number 6, where we can set like the left-hand side equal to, we'll just call it F, and the right-hand side we'll call G. Okay, so we're going to call this side F. Let's do a different color. We're going to use yellow. So this side will be our F. And then this side over here will be our G. And the trick here is going to be to write both of these as functions in terms of K. So let's go over to Desmos and say we're going to have f of K instead of f of X, because K is what we're trying to solve for, of the integral from negative pi over 2 to K cosine x dx. Okay, and then the right-hand side we'll call G of K equals the integral from K to pi over 2 cosine x dx. Oh wait, we forgot the 3. 3 times that, right? That's 3 times as big. Cosine of x dx. And find where those intersect in between. Now, the upper bound here is going to be pi over 2. So, pi over 2, if I say x equals pi over 2, this is going to be basically the right-hand boundary. And so we're looking for that intersection in between 0 and that. And we see it right here. Check it out, pi over 6. It's so much easier, but I think like conceptually it's kind of hard. I think it's hard to kind of figure out how you set this up. But look at that. We avoided all the algebra, all the calculus, kind of cheesing our way through this problem. But either way, you're going to get pi over 6. I just want to give you two methods on how you do that, kind of the long way and the short way. If you understand that short way, that can really save you some time. Number 10, this is our last problem. Last problem of the review. It's a 4-parter, but here we go. Let R be the region bounded by the x-axis, the graph of y equals root x, and the line x equals 4. So let's try to envision like what this graph actually looks like. So here's the x-axis. Y equals root x. It's going to do something like this. And then, here's x equals 4. And so square root of 4 is 2, so we know for sure that this is going to be at 2. Okay, so the area that we're talking about is right in here. Finding the area of that region, this should be, super easy problem once you, kind of look at this. We're going to find the integral from 0 to 4 of the square root of x dx. This is something that you should be able to do by hand. But we're going to get a calculator here, so we might as well take advantage of that. So let's get rid of all this. And I'll just say f is root x. Oh, I guess I don't need those parentheses. There we go. And so what I want is the integral from 0 to 4 of f dx. That's 5.333. So that would be like what? 16 thirds, I think. Let's see, 5 would be 15 thirds. Yeah, 16 thirds. 5.333. All right, part B, find the value of h such that the vertical line h divides the region to two regions of equal area. Okay, so h is going to be somewhere here. Not sure exactly where it is, but we're going to kind of approach it the same way we did up here. We're going to take the shortcut this time. Okay, we're going to say, we're going to let, here's the setup. Here's what you're going to type into Desmos. I'm going to say f of k is the integral from, oh, not k, h this time, sorry. It's going to go from 0 to h. Okay, the function here is root x dx. Okay, so that's my function h, and then I'm going to also define a function g, which is going to be the right-hand side. So we're going to go from h to 4 root x dx. We're going to see where these two things are equal. Again, this is kind of a cheesy way to get through it, but I think it's just so much easier. I don't know. Yeah. So we're going to say f of h is going to be the integral from 0 to h root x dx, and the other one, g of h, is going to be the integral from h to 0 root x dx. Oh, no, not h to 0. What am I talking about? H to 4. Did I write 0? I don't think so. Yeah, no, okay. So this point of intersection here is going to be our answer, 2.519. Okay, basically what, the equation that we're actually trying to solve here, let me move all this over, is we want the integral from 0 to h of root x dx to be equal to the integral from h to 4 root x dx. And this is just kind of our way to cheese our way through that. Otherwise, you'd have to use the fundamental theorem of calculus, kind of like we did up here, and just work your way towards it. But this is going to be a much faster way to do it, I think. Okay, letter C. Find the volume of the solid generated where r is revolved around the x-axis. Okay, so if I take this and I revolve it around, there's just one function here, right? So I'm not going to have that like circle in the middle missing. It's just going to be a bunch of disks, a bunch of circles. So recall that the basic idea here on these volume problems is to go from A to B, in this case from 0 to 4, find the area of the cross section, and then multiply by dx. So the area of the cross section here is just a circle, right? There's no hole in there. Okay, so it's just going to be a basic old pi r squared. So we're going to find the integral from 0 to 4. Okay, this radius here is going to be just the value of the function. So pi times root x squared dx. Now you should know that, of course, square root of x squared is just x. So that works out pretty nice. But yeah, we'll just type this into Desmos either way. So we've got the integral from 0 to 4 of, what was it again, pi times the square root of x squared. I know you'd probably be tempted to just simplify that and just write it as x, but I'm just gonna, make sure that I don't make any mistakes here. And yeah, I get 25.132. Because of the simplicity of this function, you probably could have gotten away with doing this without a calculator. I think this one would be doable because really just you're integrating x. You can factor out the pi, And this one actually works out pretty easily without a calculator, but yeah, I'm fine with that for now. D, the vertical line x equals k divides the region R into two regions such that when these two regions are revolved around the x-axis, they generate solids with equal values. Find the value of k. Okay, so same kind of idea here. All right, we're going to actually solve it kind of like this one. We're going to take that shortcut. Okay, the two regions are the two volumes that we want to be equal to each other. The first one's from 0 to k, and that's going to be the pi at r squared, so this root x squared dx. And we want that equal to be equal to the volume between k and, was it 4? Pretty sure it was 4. Yep, 4 pi times root x squared dx. Just to simplify this out, I think it might be worth it. We could factor out a pi and just write square root of x squared is just x. Make that pretty easy. And then also factor out the pi on the right side. Actually, this might just be easier to not try to cheese our way through it, just because the numbers here are just like the expressions here are a lot simpler to deal with. You can even see that we could divide pi on both sides to simplify this even further and say, okay, the integral of between 0 and k x dx needs to be equal to the integral from k to 4 x dx. Now let's work this on out by hand. So on the left-hand side, the antiderivative is going to be the same on both sides. It's just 1/2 x squared. So you have 1/2 x squared from 0 to k should be the same thing as the integral, the antiderivative there is going to be 1/2 x squared again from k to 4. And so if I plug in k here, I get 1/2 k squared minus 0. We're going to ignore that. Equals 1/2, let's see, 4 squared is 16, half of 16 is 8. So we get 8 minus 1/2 k squared. And if I add 1/2 k squared to both sides, I just end up with 1/2 plus 1/2 is 1. So k squared is 8, and so k is root 8. Now, if you were to have tried to approach this kind of like we did number 9 and kind of like how we did 10b, probably going to get a decimal answer. So if you're just looking to check to see if your decimal answer is correct, you would have got 2.828. So either one of those answers are fine. But that's going to wrap it up for today's review. Please reach out and let me know if you have any questions on any of these problems. Be very happy to help you out. I know, it's getting kind of challenging. We are pretty much at the end of this course. We only have a few more lessons left. Some oddball lessons that I think you'll appreciate. I don't think they'll be quite as hard as some of these. But anyway, y'all have a great night. I'll see you next time.